Hi everyone, in this part of our mass spec series, we're going to be talking about time-of-flight machines. This is not going to be about MALDI ToF, we'll get to that in the next video, but we're going to be talking about time-of-flight, and how those detectors work. And it all comes down to this beautiful equation that we've all seen before, Ke equals 1/2 mv squared. And using that idea that we learned from physics, we can separate ions in that way without having to use any magnetic fields or quadrupoles or anything. It's very simple how this is done. And you'll see with MALDI, it's actually one of the better ways to go about this. Now, what we're going to do is we're going to go through, and hopefully you've watched my other videos. If you haven't, you can learn about, this is called a, a electron impact ionizer. And if you at least know what this is, it will be really easy to understand. If not, go back, but I will give a short introduction and review. So you have molecules that go into this electron chamber. Basically, electrons are coming off of this tungsten filament. They are striking down at the cathode about 70 volts in between there. So those electrons are flying. They're going to ionize the molecules, and they're going to be accelerated in this acceleration disks through a slit, and they're going to go through this field-free region. This is the new part right here, the field-free region. Basically, there are zero forces acting on that particle at that time. You know, maybe some residual of that negative plate, but usually we can block that out, maybe with some sort of like dampening material that kind of blocks the field from moving past that point. However, in this field-free zone, the molecules are just going to drift. So they're going to be accelerated, and then they're just going to stop accelerating and go through space. Now, you want to hold this part under vacuum. Preferably all of it's under vacuum, but let's just indicate with certainty that this is under vacuum, okay? So the time-of-flight machine, under vacuum, the molecules go in and fly. So what the hell is separating them? There's no like physical moving of the stuff. It all has to come down to Ke equals 1/2 mv squared. When you accelerate these molecules, hopefully they're going to have roughly the same amount of kinetic energy. Okay, that's a given. They all have the same kinetic energy. Well, we know that their velocities are going to be different because of this m term here. Let's define three masses that are going to go through MALDI, or sorry, through the time-of-flight. I keep saying MALDI. I should not say that. We have this red particle, we have this yellow particle, and we have this blue. Let's say that this is the most massive. Maybe I should use this color. The blue is the most massive particle, where red is the smallest and yellow is in between. So a really, really heavy fragment or molecule or ion, a really relatively intermediate, and then a very small ion going through that mass spec being accelerated. Okay, so using this mass term, we know that this is going to be the slowest, right? The blue is going to be the slowest, where the red is going to be the fastest. Okay, because if they have the same kinetic energy when they all reach this point here, okay, and their masses are different, well, then their velocities are going to be different. Thus, they're going to hit this detection plate. I should have pointed out, this is a detection plate at different times. And that's what time of flight is. It's literally in the name, time of flight. Okay, so let's visualize this. Our fastest molecule is going to zoom to the end and hit the detector. So its peak is going to show up right here. And because of Boltzmann distribution, we know it's not exactly going to be at the same time. We're not going to get a very narrow, infinitely thin peak. There's going to be some band broadening to that. Okay, so that's the first one to reach the detector. And then the yellow comes through. And he takes a little bit longer, but then he shows up on the time scale. And then the blue one, the slowest one, he's going to take his time. He's going to really wait to reach that detector because he has so much mass. Therefore, he has such less velocity than the other ones. And then we'll see him elute or not elute, I guess that wouldn't be the right term, hit the detector at a different time. So hopefully you can see the difference. The faster particles hit the detector first, where the slowest ones hit them at the end. This is a really effective way and a very cheap way, because running a magnetic field, running an electric field all day can be really, really, really expensive. This, if your particles that you're looking at are just so vastly different in their mass, use a time of flight. It's relatively cheaper. And that's how it works. Hopefully you guys enjoyed this. There's not a lot else to add. If you did enjoy this, please drop a like, comment, and subscribe. I would greatly appreciate it. Hope that you have a wonderful day. Bye-bye.